Good morning, students. In today's lecture, we will discuss some important theorems related to noetherian modules. So, our first theorem is to prove that every homomorphic image of a noetherian module is noetherian. So, let us take a noetherian R module M. And let us take M dash is homomorphic image of module M. We are to prove that M dash is noetherian R module. Now, because M dash is homomorphic image of M, so by definition of homomorphic image, we have an onto homomorphism from module M into the module M dash. And this onto homomorphism we have denoted by F. Now let us take K is the kernel of this homomorphism. Then we know that kernel of a homomorphism is some module of this M. Now we have an onto homomorphism with the kernel K. So we can apply fundamental theorem of homomorphism of modules. So by fundamental theorem, the factor module M by kernel of F, that will be isomorphic to module M dash. Now kernel F we have denoted by K. So we have obtained the factor module M by K is isomorphic to M dash. Now M by K, this is factor module of M, and M is given to be noetherian. We already discussed in yesterday's lecture that factor module of noetherian module is noetherian, and therefore the factor module M by K is noetherian. Now, because the factor module M by K is isomorphic to M dash, and because this is noetherian, so M dash being isomorphic to a noetherian module will be noetherian. So this proves that M dash is noetherian. So we have proved every homomorphic image of a noetherian module is noetherian. So in order to prove this theorem, you will have to prove the theorem that every factor module of a noetherian module is noetherian. Now, in the next theorem, we will prove that direct product of noetherian modules is noetherian. So let us take two noetherian R modules, M1 and M2. We prove that their direct product is noetherian. Now, let us consider the factor module M1 cross M2 by M1 cross 0 module. Now, we already discussed a theorem related to isomorphisms in the previous section. So I am using that theorem here. So this factor module is isomorphic to the product of the factor modules M1 by M1 and M2 by 0 module. Now this product can further be written as the 0 module cross M2 by 0 module. Now this is further isomorphic to the factor module M2 by 0 module. And this factor module is further isomorphic to M2. Now, this module M2 is given to be noetherian R module. And this module, being isomorphic to M2, will also be noetherian. So we have proved that the factor module M1 cross M2 by M1 cross 0 module is noetherian. Now, let us prove this module M1 cross 0 module that is noetherian. To prove that this module is noetherian, we can define a mapping phi from the module M1 into the product of modules M1 and 0 module. To define this mapping, we can take an element M belonging to the module M1. Now, because this is the product of modules M1 and the zero module. The elements of this module are of the type of ordered pairs. Now because M belongs to module M1 and zero element belongs to the zero module, so this ordered pair M comma 0 belongs to the product of modules M1 and zero module. So in this way we have defined a mapping phi from module M1 into the module M1 cross zero module. You can easily prove that this mapping is an isomorphism of R modules. Means these two modules will be isomorphic. So we can say that the module M1 cross 0 module is isomorphic to the module M1. Now the module M1 that is given to be noetherian, and this module being isomorphic to the module M1, that will also be noetherian. So we have proved the module M1 cross 0 module is also noetherian. So till yet we have proved that this factor module M1 cross M2 by M1 cross 0 module and the module M1 cross 0 module are noetherian. Now factor module is noetherian, this sum module is noetherian, so this module will also be noetherian. So we can say that the product of noetherian modules is noetherian. Now here we have proved the theorem for two noetherian modules. We can generalize this result also. Means in general we can say that finite direct product of noetherian modules is noetherian. Means if we have the noetherian modules M1, M2, M3 and so on up to Mn, these are noetherian, then so is their direct product. So in order to prove this theorem, first of all you will prove the above theorem. Now in order to prove this theorem, we apply induction on n. So for n is equal to 2. Now because the modules M1 and M2 are given to be noetherian, R modules. So by above theorem, direct product of two noetherian R modules is noetherian. So we can say that M1 cross M2 is noetherian. So for the first step, you will prove the above theorem. Now let us suppose by induction the result is true for n minus 1. It means if we have n minus 1 number of noetherian R modules, then so is their direct product. It means the direct product of modules M1, M2, M3 up to Mn minus 1 are noetherian. Now let us prove the result for n. Now let us consider the direct product of n noetherian modules M1, M2, M3 and so on up to Mn. Now this product can be written as the product of these two modules. One of the module is direct product of the modules M1, M2, M3 up to Mn minus 1 and the other module is Mn. By the induction step, the product of n minus 1 noetherian modules is noetherian. So this module is noetherian. Also the module Mn that is given to be noetherian R module. So by first case, direct product of two noetherian modules is noetherian. So we can say that the direct product of these two noetherian modules is again noetherian. So this completes the proof of the theorem that finite direct product of noetherian modules is noetherian. Now our last theorem in the noetherian modules is to prove that sum of noetherian modules is noetherian. So let us take two noetherian R modules M1 and M2. We prove that their sum is noetherian. Now in order to prove this theorem, we will use the theorem that direct product of noetherian R modules is noetherian. Let us denote the sum of modules M1 and M2 by n. And the direct product of M1 and M2 we have denoted by n dash. Now let us define a mapping phi from the module n dash into the module n. Because n dash is the product of modules M1 and M2. So its elements are of the form of ordered pairs. So let us take an ordered pair consisting of elements A and B. Here A belongs to the module M1 and B belongs to the module M2. Now, because A belongs to M1 and B belongs to M2, so A plus B, that will be an element of module M1 plus M2. M1 plus M2 is N. So we can define the mapping image of the ordered pair AB under the mapping phi is equal to A plus B. So in this way we have defined the mapping phi. Now let us prove that this mapping phi is an onto homomorphism of R modules. So first of all we prove that phi is homomorphism of R modules. To prove homomorphism, first condition, let us take two ordered pairs belonging to the module n dash. So we have taken one of the ordered pairs AB and second the ordered pair consisting of C and D. By definition, the elements A and C, they belongs to the module M1 and the elements B and D belongs to the module M2. Now let us find the image of the sum of these two ordered pairs. Now by definition of addition, we can write the sum in the form A plus C comma B plus D. Now by definition, the image of ordered pair AB is A plus B. So the image of ordered pair A plus C comma B plus D, that will be the sum of these two elements. So that will become A plus C plus B plus D. Now this can further be written as A plus B plus C plus D. A plus B is the image of the ordered pair AB and C plus D is the image of the ordered pair CD. So we have proved that image of sum of ordered pairs is equal to sum of images of the ordered pairs. First condition for the homomorphism of R modules is satisfied. Now for the second condition, let us take an element R belonging to the ring R and an ordered pair consisting of the elements A and B from the module n dash. Now let us find the image of R into the ordered pair AB under the mapping phi. Now by definition, this multiplication can be written as R into A comma R into B. Now by definition of mapping phi, image of this ordered pair is equal to sum of these two elements, means RA plus RB. Now this can further be written as R into A plus B. Now A plus B is the image of the ordered pair AB under the mapping phi. So we have proved that the image of R into ordered pair AB is equal to R into the image of ordered pair AB. So till yet we have proved that phi is a homomorphism of left R modules. Now let us prove this mapping phi is onto. Now to prove mapping phi is onto, let us take an arbitrary element T belonging to the module N. N is the module M1 plus M2 by definition of linear sum of modules. T will be of the form of sum of elements from module M1 and module M2. So we have taken an element M1 from the module M1 and M2 from the module M2, so that T can be written as M1 plus M2. Now, because this element belongs to module M1 and this element belongs to module M2, so the ordered pair formed by M1 and M2 that belongs to the product of M1 and M2, and M1 cross M2, that is the module N dash. Thus, for M1 plus M2 belonging to the module N, there exists an ordered pair consisting of elements M1 and M2 from the module N dash, such that image of this ordered pair under the mapping phi is the element M1 plus M2, and M1 plus M2 is T, which was an arbitrary element taken from N. So we have proved the definition of onto mapping. So this proves that phi is onto homomorphism of R modules. So we can say that N is homomorphic image of module N dash. Now, because we have already proved homomorphic image of natherian module is natherian. Now, because the module N dash, that is the direct product of modules M1 and M2, and we already discussed direct product of natherian modules is natherian. So we can say that module N dash is natherian. Now N, being the homomorphic image of N dash, that will also be natherian. And we have taken N to be sum of M1 and M2. So we can say that M1 plus M2 is natherian. So this proves that sum of natherian modules is again natherian. So this completes the topic natherian modules.